So here I'm going to look at section 9.5 and 9.6. And all there is to say really at this point is here are the trig graphs and this is what shapes they are. In chapter 10 we'll look at why they're this shape and we'll get a bit of an intuitive feel for them. But for the moment we're just saying, look, here is the sine graph, here is the cos graph. There's a few features that we should be sort of doubly familiar of, so I'll point out a few bits here. First of all, sine theta, well, theta is an angle, okay? Now, at the moment, we've only really thought about theta being an acute angle, because it's supposed to be an angle in a right-angled triangle, so it's only really this part of the graph that we could work out sort of for ourselves. You know, this is the bit that intuitively makes sense, but it keeps going like this. Exactly why we can justify it being positive here and negative here and making exactly this shape we'll look at in chapter 10. But for now, let's just observe that after 360 degrees, it repeats itself. Now we'd expect it to, because if theta is an angle, it would have to start repeating after 360 degrees, because an angle of 361 degrees is the same as an angle of 1 degree, and so on. An angle of 370 degrees is the same as an angle of 10 degrees. Now that's the same again of the cos graph. After 360 degrees, it repeats itself. If we go backwards, then we can think of an angle as turning in one direction and a negative angle as turning in the other direction. So again, we're going to start repeating ourselves in the negative part of the graph. The fact that sine goes up to 1 and down to -1, well, if you think about the right-angled triangle, we've got opposite over hypotenuse, right? Sine of theta is opposite over hypotenuse. Well, if sine is a very, very small angle, then the opposite is going to be very, very small. Sorry, this is a terrible right-angled triangle, but hopefully you get the idea. The opposite is going to be very, very small compared to the hypotenuse. So when you've got a very, very small angle, your sine is going to be very, very close to 0. When you've got a very, very large angle, close to 90 degrees, then your opposite is going to be very close to the same as the hypotenuse, so it gets close to 1 and it gets right up to 1 when you actually get to 90 degrees. Now, you can't have bigger than 1 because the opposite can't be bigger than the hypotenuse. So that's how we're going to justify it not being bigger than 1. And you perhaps have heard of a sine curve as being this sort of shape, and we see them in physics and all sorts of places as sound waves and other things. So there we go, sine rule, sine and cosine. Look, this shape, we need to be really familiar with them, and that's where we're going to start getting familiar with them, is in the next two sections, section 9.5 and 9.6 of this chapter. The tan graph looks like this. Now, the tan graph actually repeats itself every 180 degrees. So if it's repeating itself every 180 degrees, of course it is repeating itself every 360 degrees as well. It's just that between 0 and 100 and 360, we actually do 2 cycles. We go up here, and then up here, and up here. So we get 2 full cycles in 360 degrees. We get these asymptotes here at 90 degrees, and let's have a look at why that happens. If you think about the tan graph, it is opposite over adjacent. So as I get towards 90 degrees, if I have a very big angle here, the opposite over the adjacent, well, the adjacent is getting smaller and the opposite is getting closer to the hypotenuse. So I'm dividing by something which is closer and closer to 0. So that's where my asymptote comes from there. So we don't limit ourselves at 1 on the y-axis, it shoots off to infinity. And then comes back in from -infinity, and we get this sort of shape. So the first thing we need to be able to do is sketch those graphs and be used to them. I suppose the last observation is that this lump here and this lump here, lump is not a mathematical term, by the way, but each of these things is exactly the same size and shape. They're symmetrical down the middle. I could rotate this graph and it would fit back onto itself around any of these points here. So each of these, 0 degrees, 180 degrees, 360 degrees are all points that we can, we have rotation symmetry order 2 for the whole graph, right? We can flip it, we can rotate it 180 degrees and then rotate it another 180 degrees and we get the graph back. And that's true of the cosine graph and of the tan graph for all the points where it crosses the x-axis as well. So just start the process of getting yourself very familiar with these graphs and how they look and being able to sketch them. You should be able to sketch them in seconds, right? So when I say sketch a sine graph, an A-level student will say, okay, sine graph starts at 0 and then does this. Cosine graph starts at 1 and then does this, and then it takes me another couple of seconds to say, well, that's 0, 90, 180, 270, 360, and so on. And if I need to, I can sketch it back here for minus 90, minus 180. That's the sort of speed that we need to be able to sketch these. That's how familiar with them that we need to be. Now, the next thing it asks us here is this sort of question. If sine of minus 30 is minus 0.5, so sine graph starts at 0. It's going to do this. Sine of minus 30, so if I take minus 30 degrees and I plug it in, I get the sine of minus 30, and it's minus 0.5. Oh, sine of minus 30 degrees. Now I want another value of sine where, so I want another angle, sine of something equals minus 0.5. Well, if I draw this 0.5 line across here, you can see there's going to be loads of them. There's one here, there's one here, there's one here. If I input this angle, I'd have got sine of that angle is minus 0.5. If I input this angle, sine of that angle is minus 0.5. Now, if I use the symmetry of this graph, this here is a line of symmetry. Well, if that's 30 degrees from that x-axis crossing point to here, then this must be 30 degrees as well. And I know that this is minus 180. So minus 180 go 30 degrees this way, so this must be minus 150 degrees, okay? Same thing over here. This lump here is exactly the same size and shape as this lump here. So if that leap there is 30 degrees, this leap here must be 30 degrees, and this leap here must be 30 degrees. And if I'd labelled my axes as 180 there and 360 there, that would help me go 180, 30 this way. So this must be 210 degrees, and this must be 330 degrees. So just using the shape of the graph will tell me that the sine of minus 150 is the same as the sine of minus 30, is the same as the sine of 210, is the same as the sine of 330. The question tells me that the sine of minus 30 is minus 0.5, so the sine of all of those different numbers is minus 0.5. And if we wanted to keep the graph going, we could obviously find infinitely many other numbers which would fit with that as well. We just got to keep drawing the graph and working out what these numbers are. Okay. On section 9.6, all they're doing here is they are saying to you, you remember those graph transformations that we looked at earlier in the book? Well, they still work for sine, cos and tan graphs. There's no exception, okay? So the sine, cos and tan graphs do the same thing. So if I've got the sine graph add minus 1, well, that's a slide of the graph down one space, so the graph's going to look here. Cos x plus a half, well, that's slide the graph up the y-axis by half a unit, so it's going to end up here. 3 times sine x, that's sine x and then times 3, so that's going to be a y change, a stretch by a factor of 3. So it looks exactly the same, but we've just got a different label on the y-axis. It goes up 3 and down to minus 3. It's that sort of thing, okay? So you need to know your stretches, your slides, your reflections. Sorry, I shouldn't say slides, should I? I should say transformations. So your stretches, your transformations, and your translations, and your reflections in the x-axis and the y-axis. Something that sometimes helps is thinking about it like this. If I have something like 4 plus sine of 3x, think about it like this. What I've done there is I've taken the x, I've timesed it by 3, then I've taken the sine, then I've added 4. So think about the order that we do these things in. That thing there is the shape. The graph doesn't get its shape from timesing by 3 or adding 4. The graph gets its shape from taking the sine. So it's the sine curve, but I've times by 3, then I've got the sine curve, then I've added 4. So everything over here is an inside the brackets thing. Everything over here is an outside. So this is f of 3x and then plus 4. So from that, we can now see that this is an inside the brackets. This is a times by 3 before the brackets. So it's a stretch by a factor of 1 over 3. It's a squash by a factor of 3 in the x direction. And then I add on 4. That's outside the brackets because it's after the bit of the graph that's given the graph its shape. So it's a slide up by a factor of 4. Sometimes students find that a useful way of thinking about it. But exercise 9G is just another graph transformations exercise. Only we're using the trig graphs to start off with. So don't let it scare you off. We're starting with a weird looking graph that repeats itself and wibbles up and down. But the graph transformations are the same as they were in the previous chapter. So that's all we have to say for chapter 9.